This is video 24 in the lecture on the design of reinforced concrete beams. This lecture demonstrates with 4 examples how to calculate the minimum reinforcement. In this example, we have a beam with a depth of 550 millimeters and a width of 300 millimeters. The point of gravity for the reinforcement D1 is 55 millimeters. D1 is here. We do this to make this exercise a little bit more easier. In reality, you do not know what D1 is because you don't know AS1, the reinforcement AS1. So you assume a reinforcement AS1, for instance, a diameter 20. You do the calculations, you find the minimum reinforcement, and then you check if D1 is correct. If not, then you redo the exercise with the correct D1. But for this exercise, we take D1 equal to 0.1 times the total depth of the beam. So if you do not know anything, for beams, it's common use to take 1/10 of the depth of the beam. The question here is, what is the minimum reinforcement? It's a beam subjected to bending. First, we look at crack control. This was the formula for crack control. Kc, it's load case pure bending, so Kc is 0.4. The form factor, it's just a function of D, and it's equal to, or the shape factor, it's 0.825. FC effective is equal to the mean tensile strength, and it's equal to 2.9 megapascal. The area under tension of the concrete is, because it's bending, it's half the area, which is 82,500. The maximum steel stress is 500 because there is no specific crack width stated in this exercise, so sigma s can be taken as 500. And then AS min, just using this formula, gives you 158 square millimeters, or 2 diameters 10 will be fine. This is for crack control. So we start for the minimum reinforcement due to brittle failure. We've seen that this is the formula. We already know FCTM and B and D, so the minimum reinforcement is 2 diameters 12, but there is a limit to it, a lower limit. It's 0.13% of the section, which is 193 square millimeters. So the resulting minimum reinforcement is the maximum of crack control and the maximum of brittle failure. And you see that brittle failure here is dominant, not that 224 square millimeters or 2 diameters 12, it's dominant because sigma s is equal to 500 megapascal. Now let's take a second example. It's a similar section, cross section, but now we will calculate the minimum reinforcement for a crack width limit of 0.3 millimeter, which is not much, it's just 0.3 millimeter. So first we start with crack control. We got this formula. Kc was for bending is 0.4. The shape factor stays at 0.825. FCTF equals FCTM, it's 2.9 megapascal. The area in tension is half the section. And this time sigma s is not 500. Why? Because we have said, okay, we need a crack width limitation of 0.3 millimeters. So the table 7.2n of Eurocode 2 part 1.1 we will use, but first we will check if this table has to be adapted, yes or no. And we see that 0.1 times h equals d1. So this is okay, and FCK is 30, so FCTM is 2.9, so that's okay. So we can use the table as is without any change. For a crack width limitation of 0.3, we look at a diameter of 10 millimeters and we see that the maximum allowable steel stress is 320 megapascal. So we use again this formula, but instead of 500 we use 320 megapascal and we have 3 diameters 10 instead of 2. So for crack control we need 3 diameters. Brittle failure, we use this formula and we arrive at also 3 diameters 10. So the resulting minimum reinforcement is the one for crack control and brittle failure. Now you will see that because we have a limitation, a crack width limitation, now suddenly the reinforcement for crack control is dominant. Of course, if you round off, this is 3 diameters 10, crack control is also 3 diameters 10, but that's coincidence. But if you look at this, you will see crack control was now dominant. So if you impose a crack width limitation for minimum reinforcement, the formula for crack control will most likely be dominant. The third example, you have, for instance, some masonry and a roof in reinforced concrete, and this is the edge of the roof. So this is a non-bearing beam, and it's just an edge beam of a slab. And it's in concrete grade C2530. The depth is 850 and the width is 140 millimeters. And we will use a point of gravity for the reinforcement equal to 40 millimeters. The question is, what is the minimum reinforcement for this beam? And make a sketch of the reinforcement. We use first crack control. KC, it's not bending, it's pure tension, because it's pure tension caused by restraint deformation. When the beam is poured, it's on top of the masonry will have a restraint, will restrain the hardening of the beam. So we use pure tension here as a load case. So Kc is 1, the shape factor is 0.65. FCTF equals FCTM, it's for C25, so it's 2.56 megapascal. The area in tension is now the total area, because it's pure tension. So it's not half the area, it's the total area. And there is no specific crack width stated, so sigma S is 500. And we see that we have 300 or something like 400 square millimeters. It means 8 diameters 8. Because this is pure tension, the reinforcement must be put in the whole section and redistributed in the whole section. So that's 8 diameters 8. For brittle failure, we have our known formula. Well, in longitudinal direction, because the beam is not carrying any force, so brittle failure we do not fear here. So there is no danger on brittle failure, so we do not have to take this into account. We now will try to make a small sketch. This is the edge of the roof. We put the 8 diameters 8 around it, and we check if the maximum distance between 2 bars should always be less than 300 millimeters. So if we check this, we see it's 257, it's okay. If not, you have to put some extra bars in it, or use a smaller diameter with a larger number of bars. Example 4, it's a similar exercise as the previous one, but now we have crack width, a maximum crack width of 0.2 millimeters. First, we look at crack control. The load case is pure tension because it's restraint deformation. The beam is not loaded, it's not bearing. So Kc is 1, the shape factor 0.65. FCT effective is 2.56 megapascal. The area in tension is the whole section, And sigma S, well, for sigma S, we have a crack width limitation of 0.2 millimeters. We check if the table should be adapted, and we see for H minus D equals 0.1 H, so that's okay. But FCTM, it's not equal to 2.9 because the concrete grade is C25 instead of C3037. So we have to adapt this table 7 to N. What we now do is we calculate the correction factor. It's a correction factor for tension, a load case tension, and it's 1.1. We have chosen a diameter 10. We divide this diameter by this correction factor and have 9. With this 9, we look at table 7 to N and make an interpolation, and we find that for a crack width of 0.2 millimeters, the maximum steel stress, allowable steel stress, is 270 megapascal. Then we use our formula and we have 8 diameters 10. For brittle failure, again, there is no danger for brittle failure, so we will leave this out. The center to center of the rebars must be smaller than 300 millimeters. So by checking that, we see that 8 diameters 10 will be all right. You see now the difference directly. Instead of 8 diameters 8, we have now 8 diameters 10. That's only because we limited the crack width. So remember, using a limit to the minimum reinforcement consumes more reinforcement.